And without further ado, I would like to present our amazing speaker tonight, Dr. Thomas Peterson, who is a Nobel Peace Prize winner and co-author of more than 100 papers. Thank you.
Thank you very much, and thank you for the warm welcome. Is this, yeah, this sounds like it's coming through fine. If I get too loud or too soft, signal me a little bit. So, the topic of the talk is what is science? And I'm not going to tell you what is science based on just my own opinion. This isn't just my opinions, but rather I'm going to try to weave this talk together using a series of quotes that I've collected over the years and saved out from somewhat eclectic reading. So the topics we're going to hit are the scientific method, how some of the basics of science, how it builds on itself, and how science is always tentative and it's self-correcting, and how it differs from law and differs from art. Then I'm going to talk a little bit about the role of emotions in science, and then some obstacles to understanding science. And lastly, we'll hit on a way to rate claims and a final comment that I hope you will take to heart in the future when you hear talk about science. So the scientific method, when we were in high school, we all learned that the scientific method was you set up you have a hypothesis, you conduct an experiment, and you get results. It's a bit more complicated than that. Sir Peter Medawar, a Nobel laureate biologist in 1969, wrote, "Ask a scientist what he conceives a scientific method to be, and he will adopt an expression that is once solemn and shifty-eyed." Solemn because he feels he ought to declare an opinion, shifty-eyed because he is wondering how to conceal the fact that he has no opinion to declare. And that was from a Nobel laureate. Michael Shermer, the director of the Skeptics Society, in 1997 said, "There is a sizable literature exists on the scientific method, but there's little consensus among authors." And one of the reasons is summed up in another quote from Michael Shermer, that it is not possible to say which came first, the hypothesis or the observation, since the two are inseparably interactive. And that's certainly been my experience. I will start out with a hypothesis and start doing analysis of the data. And then as we go forward, I get some preliminary results, which will then alter my hypothesis, which alters the test I'm doing, and there's a big give and take going on there. Isaac Asimov is credited with saying a really nice quote, except I couldn't actually find a reference to where this appeared. So it may be apocryphal rather than actually written by him. But he was a biochemist before he turned a science fiction writer. The phrase, the most exciting phrase to hear in science, the one that heralds the most discovery is not eureka, but that's funny. And it is. When I got my master's in cloud microphysics, and then I decided to switch to satellite climatology for my PhD. And I talked to a potential advisor who did become my advisor, Thomas Vandahar at Colorado State University. And he asked me the question, what did you learn on your master's that will help you on your PhD? And I told him about how I was looking at the data and stuff, and I didn't think it would really be able to show what I wanted to be able to analyze and figure out. And then based on some other advice I got, I just realized I had to just jump in and charge ahead and work on it. And it all worked out. And he said, that was really great. I've seen too many graduate students sitting around expecting a light bulb to show up above their head like you see in cartoons, and that isn't how it works. You have to charge in and dig on it. So science basics. We'll go with the astronomer Carl Sagan in 1996 said, "Science is more than a body of knowledge. It is a way of thinking." So if you're reading USA Today and they have a little blurb that says, here's some science factoids. No, science isn't the factoid. Science is a way of thinking that proved the factoid correct. And the key to that is testing. Michael Shermer again, science which I define as a set of methods designed to describe and interpret observed or inferred phenomena, past or present, and aimed at building a testable body of knowledge open to rejection or confirmation. In other words, science is a specific way of analyzing information with a goal of testing claims. The great philosopher of science, Karl Popper, in 1934 put it this way: insofar as a scientific statement speaks about reality, it must be falsifiable. Insofar as it is not falsifiable, it does not speak about reality. So there has to be a test that you can prove it false. So if you go to Aunt Mildred's house and she tells you there are 3 ghosts living in her closet, and you realize there is not a single test you can do to prove that there's no ghosts living in her closet, then according to Karl Popper, it's not only is it not scientific, but it doesn't speak about reality. And I know that's kind of a hard statement to make in Asheville, but that's it. So science builds on itself. That's the next topic. Michael Shermer again. Scientific progress is the cumulative growth of a system of knowledge over time in which useful features are retained and non-useful features are abandoned based on the rejection or confirmation of testable knowledge. So it grows and builds there. And even as far back as 1676, mathematician and scientist Sir Isaac Newton wrote in a letter to a friend, he said, "If I have seen further, it is by standing on the shoulders of giants." So if he recognizes science was cumulative back in 1676, we certainly do today. Yet at the same time, science is always tentative. Carl Sagan again, discussing Sir Isaac Newton in a bit. The laws of motion and the inverse square law of gravitation associated with the name of Isaac Newton are properly considered among the crowning achievements of the human species. One of the great findings of Albert Einstein's special and general relativity is that Newtonian physics breaks down at high speeds and strong gravities. So we think of gravity not just a good idea, it's the law. But even the law of gravity breaks down when a particle passes near a very heavy object like a star, and it's traveling at speeds approaching the speed of light. Stephen Jay Gould, a geologist in 1999, wrote that science does not deal in certainty, so fact can only mean a proposition affirmed to such a high degree that it would be perverse to withhold one's provisional assent. And as you can imagine, for somebody who has been working in a climate change field, I've met many people perverse enough to withhold their provisional assent to some really solid science like CO2 warming the planet. And I was sitting next to somebody on an airplane once, and she asked me what I did, and I explained to her, and she said, "Is, global warming real?" And I said, "Yes, it's as real as evolution, that you can't understand botany, biology, or even most of medicine except in the light of evolution." And she turned to me and said, "Yeah, I don't know if I believe in that either." But the reason you can give your provisional assent is because science is self-correcting. Carl Sagan, again, from 1996, "It makes no difference how smart, august, or beloved you are. You must prove your case in the face of determined expert criticism. One of the great commandments of science is mistrust arguments from authority." But then he goes on in a parenthetical expression to say, but scientists being primates and thus given to dominance hierarchies, of course, do not always follow this commandment. But then again, you have to believe in evolution for that. So Albert Einstein, Nobel laureate theoretical physicist in 1931. So this is 10 years after Einstein won his Nobel Prize in physics, and a book was published entitled 100 Authors Against Einstein. And when somebody asked him about it, he said, he is said to have remarked, "Why 100? If I were wrong, one would have been enough." But the implication in that is that one would have had to have proof in the form of some testable results. And the Intergovernmental Panel on Climate Change in 2007 put it this way: in practice, contemporary scientists usually submit their research findings to the scrutiny of their peers, which includes disclosing the methods and data which they use, so that their results can be checked through replication by other scientists. The replication by other scientists is important. But in full disclosure, I should say that I credit this to IPCC because it was published in the IPCC, but Richard Somerville and I wrote that section of it. But it's much more impressive to say it was part of the IPCC, which, as you can see, won the Nobel Peace Prize with Albert Gore in 2007. And I want to comment on this briefly, that Alfred Nobel was a Swedish chemist and inventor. For example, he invented dynamite and also made a fortune in the manufacture of weapons. And so when he passed away, he bequeathed his fortune to the Nobel Prizes to work on that. And when the IPCC was awarded a Nobel Prize, the head of IPCC sent us all an email that said, "This means you are all Nobel laureates." And this was exciting, heady times. And then about 6 weeks later, they had the ceremony in Oslo or Stockholm? Stockholm. Anyway, they had the ceremony. I wasn't invited, but they had a handful of people. So they had the ceremony, and then a short time later, the second in command of IPCC sent out an email saying, "Some of you are claiming to be Nobel laureates. You're not Nobel laureates. IPCC is a Nobel laureate." So some of my family views it that I was a Nobel laureate for 6 weeks. But the reality was I never was a Nobel laureate, and I'm very careful not to claim to be a Nobel laureate, despite what introductions in the Citizen Time might write. I did, however, get this nice plaque on my study wall from the IPCC. So now back. You're applauding me not being a Nobel laureate. I appreciate that. So now back to science is self-correcting. Thomas Huxley, around 1880, was a zoologist, wrote that science is organized common sense, where many a beautiful theory was killed by an ugly fact. And now we get to talk about how it differs from law. Richard Feynman, the Nobel laureate physicist in 1988, said, "If you're doing an experiment, you should report everything you think might make it invalid, not only what you think is right about it, other causes that could possibly explain your results." In the law, this isn't quite the approach they use. And let me give you an example. I served on a jury, and the defendant was accused of driving in the countryside between here and up to Boone and going to rural mailboxes and just opening them up and taking the mail. And if there was a check in the mail, they cashed it. And if there was a box of checks in the mail, it was a bonanza. And so the defense called a character witness. And they asked the character witness, "Well, where do you live?" "I live next door to the defendant." He said, "How long have you known her?" "I've known her all her life." He said, "Well, what kind of a person is she?" "Oh, she's as kind and honest and just and noble as you could ever hope to have in a neighbor and a friend. She's just a wonderful, wonderful person." Then the defense rested, and the prosecutor came up and said, "What's your relationship to the defendant?" She said, "Oh, I'm her mother." Science doesn't work like that. We have to provide all that information so that people can understand it better. And now a little bit about how science differs from art. Sidney Hook, a philosopher in 1943, wrote, "Raphael's Sistine Madonna without Raphael, Beethoven's sonatas and symphonies without Beethoven are inconceivable. In science, on the other hand, it is quite probable that most of the achievements of any given scientist would have been attained by others working in their field." This is a rock-solid true statement, but it's also really humbling for a scientist. You think you're doing good work, but you realize if you weren't doing it, somebody else would have. It's inconceivable now that we wouldn't have understood the laws of gravity that Sir Isaac Newton discovered. But, you know, we may be doing it better than other people and maybe faster, or maybe actually worse. But it would have been discovered by somebody else. When my PhD advisor told me my job was to think of the world of knowledge as a giant balloon, and my goal with my PhD dissertation was to push it out just a little bit in one spot. So we're trying to increase the human knowledge. On this topic, Michael Shermer, in 1997, wrote, "Science seeks understanding through objective methods. The arts seek provocation of emotion and reflection through subjective means. The more subjective the endeavor, the more individual it becomes, and therefore difficult, if not impossible, for someone else to produce. The more objective the pursuit, the more likely it is that someone else will duplicate the achievement. Science actually depends upon duplication for verification." And indeed, I was working on a synthesis report, and we were dealing with a chapter on climate and health. And one of our author teams, we had a really good article that was solid and important to include, but one of our author teams kept saying, we can't put too much emphasis on it because it's just one article on the topic. We really need more to really feel like we can really put a lot of trust into that. So in science, you require duplication for verification. But in the art world, duplication is called forgery. And now the role of emotions. Carl Sagan in 1996 said, "In its encounter with nature, science invariably elicits a sense of reverence and awe." And that's certainly the way I feel. I mean, I got into climate science, partly to try to understand how the world works, how the climate system works. And it does elicit reverence and awe. Too many people, I think, are seduced by the Star Trek Mr. Spock model of science, that you think that your science is just all logic and no role of emotion in it. And that's actually impossible. And the proof of it impossible is a quote here from Daniel Goleman, a psychologist, in 1996. "The surgery to remove Elliot's tumor had severed the ties between the lower centers of the emotional brain, especially the amygdala and related circuits, and the thinking abilities of the neocortex. Elliot's thinking had become computer-like, able to make every step in the calculus of a decision, but unable to assign values to the differing possibilities. The result was a muddle of indecisiveness." And indeed, some of the best scientists I know have a high level of emotional intelligence. But there are obstacles to understanding science. For that, we'll go to social psychologist David Dunning from an interview he gave in 2014. "In many areas of life, incompetent people do not recognize, scratch that, cannot recognize just how incompetent they are, a phenomenon that has become known as the Dunning-Kruger effect. Logic itself almost demands this lack of insight. For poor performers to recognize their ineptitude would require them to possess the very expertise they lack. To know how skilled or unskilled you are at using the rules of grammar, for instance, you must have a good working knowledge of those rules, an impossibility among the incompetent. Poor performers, and we are all poor performers at some things, fail to see the flaws in their thinking or the answers they lack." And in climate science, we see the Dunning-Kruger effect often in blogs and comments and nasty emails that I would receive, where people are sure that they understand the science much better than the scientists working on it. But it then presents a challenge in communicating science. And scientists, we like to think that if we just could fill up this ignorant mind with all this knowledge and information, the problem would be solved. They'd be able to move on faster. But we've been teaming up with communication experts because it's a little more complicated than that, which is perhaps one of the reoccurring themes here. It's a little more complicated than that. So another quote by David Dunning in 2014 is, "An ignorant mind is precisely not a spotless empty vessel, but one that is filled with a clutter of irrelevant or misleading life experiences, theories, facts, intuitions, strategies, algorithms, heuristics, metaphors, and hunches that regrettably have a look and feel of useful and accurate knowledge. So we're all facing this when we have problems dealing with something that we're not an expert in. We have a lot of opinions and things that we've built up. But there are ways to rate scientific claims, even if you're not an expert. And I'll give you 5 criteria that Theodore Schick Jr. wrote in 2001. He's a philosopher. So 5 claims. Number 1, or 5 criteria for rating a claim. Number 1, testability. Can it be proved false? This is straight out of Karl Popper, which we discussed already. Number 2 is fruitfulness. Does it yield observable, surprising predictions? So for example, if you have a theory on why the climate is changing, and it only explains the recent surface warming for the last 50 years, that doesn't provide an explanation for a surprisable prediction. But in the analysis of the radiative properties of CO2, one of the prediction was that as CO2 warms the surface of the planet, the upper atmosphere, the stratosphere, CO2 would actually cool that. So that was a somewhat surprising, counterintuitive prediction, and the stratosphere is indeed cooling. The third is scope. How many different phenomena does it explain? So again, for that example, if your explanation only covers the last 50 years of surface warming, you know, CO2's effect on climate also explains why the Carboniferous period 300 million years ago, which was before dinosaurs, you know, was so warm. They had twice the CO2 in the atmosphere that we do. The fourth one is simplicity. How many assumptions does it make? CO2 warming the atmosphere is that CO2 absorbs infrared heat radiation and re-radiates it out, thereby warming the surface. There's another theory for climate change about cosmic rays. And the theory is you have a change in cosmic rays over time. So first you have to have a change that matches how the climate is changing. And that's dependent on the solar wind and the Earth's magnetic field. So how many cosmic rays, as well as the background radiation, are hitting the Earth. Then the cosmic rays have to interact with molecules in the atmosphere and form cloud condensation nuclei. And then a cloud has to form on those extra cloud condensation nuclei. And then the cloud has to have other properties in it that it might have formed otherwise, but with extra cloud condensation nuclei, the droplets tend to be smaller, so the coalescence slows down, so the cloud can last longer, and smaller droplets are brighter, so it can reflect more sunlight to outer space. So it's an interesting theory, but it's not simple. There's, you know, any spot along that line could interrupt the chain of events, and you need all of them to hit. And the fifth and last one is conservatism. Is it consistent with our well-founded beliefs? And science builds on itself, as we talked about. We have well-founded beliefs. CO2's role in climate has been known for over 100 years as part of our well-founded belief. And now a final comment. This is from Carl Sagan. It's one of his most famous from 1980. And it applies not only in climate change aspects, but in just about all aspects of our lives. When you read something on social media, or you read something in a newspaper that this changes everything, you know, keep this statement in mind. Extraordinary claims require extraordinary evidence. Thank you.